here is going to be a half h into, I believe this one I can combine with that, and we have here y naught plus yn, because we have only one yn. So to candidates, today we have a topic called called trapezium rule, one of the numerical topics, and we call it trapezium rule. So we say trapezium rule is a numerical method or technique, is a numerical method used for approximating area between two curves. For example, area between the curve y equals to f of x and the x-axis, and the x-axis is simply the curve or straight line in y equivalent to 0, whose exact value can be obtained using calculus, and specifically here we refer to integration. And to be straight, area, the exact value for area is equal to the integral from a to b of f of x with respect to x, where y is the curve f of x, and this is only valid for x between this. So here we mean that this x ranges between the domain a to b and it's a continuous one. So if f of x is continuous over this continuous domain, then the exact value for area is given by that. Now with this technique we are trying to simply approximate the area close to that using this rule. How do we use this rule? For this rule to start, for this method to start, we use the following. We use the following assumptions. Y equals to f of x is continuous over the domain a raised to x raised to b. So this f of x, for the first case, it must be a continuous for ax between a and b, and the curve and the area can be illustrated as follows. And the area can be illustrated as follows. Now, so the curve, the region we can illustrate, for instance, if I call this the x-axis and this is my y-axis, and I have the curve, for instance, this one here. So this is the curve y equals to f of x, and Maybe I'm interested in the area between this A and this B, and then this B. So the X values range between A and B, and the area I want to find is this one here. So the area that I want to find here, when we are using calculus, it is purely the integral from A to B of that function f of x. Now, with the numerical techniques, what we do is we subdivide this region into, so I can write this, we subdivide the region, let me say the shaded region into small trapezoidal strips of equal intervals called sub-intervals, and sometimes we say all strips. Now let me take you through this that I'm calling strips. I can have my curve here and my y. I'm just trying to bring back my curve, and then this is my x-axis, and I have this. So the curve I have there looks like this, and this is the curve we are calling y equals to f of x. Now what we do is we identify the region which is between A and B, the way we see this. Now we subdivide this. These are what we call small strips, and these strips we are subdividing the ones we are calling trapezoidal strips. So each of these strips here represent what we call a trapezium. So when you look at this first one, it is more or less a trapezium, but when you look at this curve, it gives us an error if we take an assumption that this is a trapezium, because if I remove one of it, its shape will be like this, and the shape of a trapezium is purely these straight lines. So what we do here is, as you increase the number of these strips, that means this error will almost be negligible. So what we are saying is, if from here up to here is called maybe y naught, and from here up to here is maybe yn, maybe to my students who are far, let me try to expand this such that you are able to see clearly what I'm trying to talk about. So I'm improving on the sketch. This is the y-axis, and this is my x-axis. Okay, so we are saying this is what we have as the curve y equals to f of x. Now with this, from A we are subdividing this into smaller strips, very many of them, up to the nth one, maybe can call it here, like this. Okay, so with this we are saying we are going to use the same intervals. Now when you are looking at this, there is a very small interval that you check. So from here up to here is the same as from here up to here, and it's the same as from here up to here. Remember the total distance from here up to the other side, the total distance here, remember B is the displacement from the origin, and also A is the displacement from the origin, meaning the distance between this and that, because you're only interested in this area here, is always B minus A, the whole distance. Now we divide this in such a way that the distance from here up to here is the same as from here up to here, and this one form the number of strips, implying that If I want to get this, the one of it, which we call from here, each of this is height h. Each of this is height h. So with the very many of them, so this height h will simply be equivalent to get the whole of this distance, which is b minus a, and then we divide this by the number of subintervals you are forming, and that is n. So this is the formula for getting each of this height. Now, back at what I was illustrating here. If from here up to here is y0, and from here up to here is y1, this is y2, and so forth. Maybe this is y3, and very many of them. This one is going to be the last one here, it is yn, and this one is the same as yn minus 1 backwards like that. There are very many of them that we are assuming in that. Now, to get the total area here, we first assume this is a trapezium, this is a trapezium, this is a trapezium, this is a trapezium. We don't consider the whole of this. We choose to work with each trapezoidal strip. Now, when I check the first one, remember, if I have this, if you can recall the primary work or any class or level, if this is A, and then the distance between the adjacent sides is h, then how do we get the area of the trapezium? The area of a trapezium is usually given by a half h, the distance between, then times a plus b. Now, with this, we are going to get the area of this. We add on the area of this. We add on the area of this. When we add all these ones from A to B, then that will be the formula for calculating the area under this curve. So following our sketch there, the first one we can call it area A1, and the area A1 we are going to get, of course, one of the side we are using the formula is going to be a half, then the height, then into the first side, adjacent side is y0, then the other one is y1. Then when we come to the second one, the second strip, it has a half of h into, that will be y1 plus y2. When you go to the third one, it is going to be a half h into y2 plus y3. Now, there are very many of them that we cannot finish. Let's now go to maybe the area an minus 1. This is going to be a half h into, this one, of course, is going to be yn minus 2 plus yn minus 1. Then when I go to the last one, maybe that is the nth area, it's going to be a half h into yn minus 1 plus yn. So these ones, when we add all of them, we are simply going to achieve, so the total area is going to be a1 plus a2 plus a3 plus up to the nth one. In some books you will find when area we can write it as simply in sigma notation. Maybe we use I equals to 1 up to n, and then we put here ai. So we are simply going to add up all this, and then we get that as the area, the approximate area for that curve and the x-axis. Okay, now let us go into this calculation. So our area is simply going to be a half h into y0 plus y1 plus a half h into y1 plus y2 plus a half h into y2 plus y3 plus up to, we have also a half h into yn minus 2 plus yn minus 1, and lastly is a half h into yn minus 1 plus yn. So that is the total area under that curve, and this a is simply going to be, I think the common elements there, we see a half h. A half h is the common element, so I'm factorizing out half times h. Now, when I factorize out this, here I remain with y0 plus y1. Here I remain with y1 plus y2. Here I remain with y2 plus y3 plus here I remain with yn minus 2 plus yn minus 1 plus this is I remain with the yn minus 1 plus yn in total. Now, when you try to look at the terms I'm adding in here, we see that y0 appears once. But y1 and y1, there are two of them. So we are simplifying this as yn plus, this is 2y1. This one we also have 2y2 plus 2y3. And the pattern continues. And when we reach here, up to plus, I think this one will have also 2yn plus 1, then plus yn. And our area is going to be a half h in 2. I believe this one I can combine with that, and we have here y0 plus yn, because we have only one yn, plus twice in 2. I think here 2 is common. y1 plus y2 plus y3 up to plus yn minus 1. Now this is what we call the trapezium rule. So this is called the trapezium rule. The trapezium rule. The trapezium rule for approximating area under the curve y equals to f of x for a less to x less to b, and where h is the same as b minus a over n. Now for this case, what is our n and what is this? So h is simply the height. And sometimes we call it with the delta of x. And it represents the vertical displacement and the divisions. Now n, this one, this is the number of sub-intervals. The number of sub-intervals, or we can call it trapezoidal strips, or we can call them strips, like that. Now, in any sub-intervals, there are n plus 1 ordinates. And this is some of the areas you need to know. So while using trapezium rule, we commit a numerical error which depends on number of sub-intervals. The error can be improved as h tends to 0. As n tends to 0. As this divisions here become smaller and smaller, then the error is always improved, or simply increasing number of, you can say, strips, sub-intervals, or you can say ordinates, or ordinates, like that. Now, let us go into examples. Let us go into examples. So example number 1, we are going to say, use trapezium rule. Trapezium rule with 5 sub-intervals. With 5 sub-intervals to find the integral from 0 to 1 of x squared with respect to x, correct to 3 decimal places. Now, using the trapezium rule, now the rest of the work we've done is part of what you need in order to handle this. And the first thing to do is to know the function you are dealing with. So this is the function. Of course, integral represents the area of the curve between two quoted limits. And for that case, we know that our f of x is equivalent to x squared. So this is our solution. So f of x is equal to x squared. And after writing this, we now say h is obtained by getting b minus a out of n, where b is the upper limit, a is the lower limit, and n is the number of sub-intervals. So my h is going to be, our b, the upper limit is 1, minus the lower limit is that, over the number of sub-intervals here, we have 5 in the equation. Now, when you compute this, which answer do you get? This is 0.2. So that is now the height. Now to candidates, when they are marking this work, this one now earns you already 1 mark. So it is a bonus mark that brings you to what we need. Now this is going to be something like the height, or simply the interval. So what we do, we now write here x, we now write here f of x, then we form a table. We form a table. Now this table here, we are going to now start from the x values range from 0 to 1. So we start here 0.0, that is the first one. The next one we keep adding 0.2. So when I add 0.2 on this, I'll have 0.2. When I add 0.2 on this, I'll get 0.4. Keep adding that same interval of 0.2, starting from the lower limit, which was 0. Now we add up this. Next is this, followed by 0.6. When I add again 0.2, I get 0.8. And when I add again 0.2 here, I will now get 1.0. Now, after getting this is now our table. We are going to now record here the values of f of x at different values of x. Now the first one here, we now go and substitute here. We are getting f of x values. Remember, it is given by x squared. So we are simply going to substitute. The first one, we are going to have f of 0, and that will be 0 squared. And that is the value we write here. So 0 squared is going to be 0. Then the next one, we're going to have what? F of 0.2. What is 0.2 squared? 0.04. Next, when I put this one here, what is 0.4 squared? 0.16. When I again substitute 0.6 here, I'll be getting 0.36. When I substitute this one there, I'll be getting 0.64. And lastly, when I put there 1, I'll be getting 1.0. Then we need to add up these values. Now this value which we have first is the one we call the y naught. This is with the usual y naught. This is the y1. This is the y2. This is the y3. This is the y4. This is the y5. That's why we said we have 5 sub-intervals. Now when I add up here, summation, you now add this first value plus the last value, and the answer here will be 1.0. Then let us add this plus this plus this plus this. Which answer do we get here? 1.20. So we get 1.20. And after that, we now come and then use the trapezium rule. So the trapezium rule for approximating area, the formula is a half h into y naught plus yn plus twice into y1, y2 up to yn minus 1. So that is how we get the area. Now, where is y naught? Y naught is the first value, yn is the last value, which is here, and then the middle ones are the ones multiplied by 2. So the first value and the last value we have already added, and we have the value here. The middle one is 1, 2, 3, 4. This one we have added, also we have the value here. So when we come to this, the integral from 0 to 1 of x squared with respect to x is now going to give us an approximation of a half times h. Our h we obtained as 0.2. Then into our first value y naught plus yn, we already added y naught plus yn. The answer is here. Which is 1.0 plus 2 into what is y1 plus y2 plus up to here. The values are here, 1, 2, 3. We added, we got 1.20. Then the remaining work is to numerically compute using your calculator. This value here will give us 0.1 into, when I add up this, the value inside here is going to be, that is 2.4, 3.4. And finally, when I simplify this times that, I'll be getting 0.34. Now this is the approximation for finding this. And this one, as I have to write to how many decimal places?